All right, we are going to move on now and finish this up. We have a few more types of decay, nuclear changes we want to talk about. And I say nuclear changes because one of these very often we call radioactive decay, but it's not really. So we've done alpha, we've done beta, let's talk about gamma. Well, gamma decay are photons that are emitted from a nucleus. And I'll kind of start near the end. If I were to write the symbol for a gamma ray photon, I can use that. That's the way I do it. What numbers would I put? That's a real brain tickler, isn't it? Anybody want to stick their neck out and tell me what numbers we should put there? No one, eh? What's the charge on a photon? A photon. It's a particle of light. Anna? Doesn't have a charge. So the bottom number is 0. How many nucleons, which is the top number, how many nucleons are in a photon? None. This is it. So as I said, I'm kind of starting at the end here. If I told you I'm just going to make one up. I don't know if this undergoes gamma decay or not. I'm going to say bismuth 210, I think that's 83, undergoes gamma decay. What's the daughter nucleus? Be bismuth 210. So again, I'm going to reveal all of my notes to you in a second, but this bismuth 210 that we end up with is different in some way than the bismuth 210 that we started off with. It has to be. One of the ways it's different is it has less mass, because a gamma ray photon has energy, and the energy has been removed from the system. What we will often do or write, and you will see this today, is you will put an asterisk on the original one that's not stable. So why does alpha decay occur? Alpha. Because the arrangement of nucleons in something like polonium-210 is not a stable arrangement. There's a more organized way to pack the nucleons together, and it doesn't involve the 4 that make up an alpha particle. Why does beta decay occur? Because one of those neutrons in the nucleus happens to be unstable, so it decays into a proton and an anti-neutrino and a beta particle or electron. Why does this bismuth 210 with the asterisk decay? Because it's not as stable as the one over here. So the big difference is the bismuth 210 on the left is not as stable as the one on the right. The one on the right is more stable. By the way, that would mean it has a higher binding energy holding it together. And that has to do with the fact that its mass is even less than the mass to begin with. Don't try to sort out all of that. I'm just pointing out things that if we follow the rules of more stable means release of energy, that's the consequence of it. So how is it more stable? Well, it turns out that there are energy levels within nuclei, and this is not a picture of the nucleus. Remember when we had energy levels for electrons, that they could be here, here, or here? You understand that was just a mathematical graphic, right? Atoms don't look like that. It's just saying this is the energy the electron can have, or this, or this. Similarly, the energy level diagrams for nuclei are not telling you what the nucleus looks like. They're telling you what some stable energies of the nucleus are. In excited states, so if I have an energy level diagram for a nucleus and it's in an excited state, the simplest explanation I can give you is all of the nucleons are a little bit further away from each other. I would say this to you though, and I hope it helps. In an excited state, which means not stable, in a not stable state, those nucleons are not packed together efficiently. And I've used this analogy for a long time. I haven't moved in a while, but I used to move around a lot. It seemed I would always be renting somewhere else or buying some other place. And there was always that box or two of junk that was the last load of crap to leave my apartment and go to the next place. You imagine what I'm talking about here? Just there, like throw it all in there. And I put it in the back seat of my car and I drive to the new place. When I get there, the stuff is, it looks like there's less stuff in the box because it's all kind of shifted and settled down to a more stable arrangement. That's what's physically happening here. We have a smaller binding energy holding the nucleus together, so it's not held together as tightly. And as a consequence, when it goes to that more stable state, things shift. All of those nucleons shift slightly and get closer together. It's a more efficient arrangement of the nucleons. And again, there's formulas for all this, but we're not going to get into it. What we can say is that if it's more stable, it has to release energy. The energy is a photon. And if it's more stable and it releases energy, it loses mass. The photon doesn't have mass. The nucleus itself has less mass. So this is a diagram from the margin of your textbook in this section. This is an energy level diagram for carbon-12, for the nucleus of carbon-12. And the question is, how do these energy levels differ from those electron energy levels in hydrogen? And I'm not talking about the numbers. What is significantly different here about the energy states in this energy level diagram compared to any of the electron energy level diagrams we've looked at? Hoping somebody sees it. Craig?
It's mega electron.
It's millions of electron volts. That's right. Remember, electrons fall in atoms, and what do they produce? Ultraviolet photons. Little tiny photons. Visible light, even simpler, tinier photons. Infrared photons. The energy changes here are so great, you produce gamma ray photons. It's just instead of an electron falling down, all of the nucleons fall down, so to speak. So, cobalt-60 undergoes gamma decay with a photon energy of that. Write the decay equation. That's 27. This cobalt is excited. That just means it has more energy. By the way, you know how you can take an atom and smack it to excite it to a higher energy? You can't excite a nucleus to a higher energy by hitting it. It's in the higher energy because that's the energy it was in when it was formed, either in the formation of the universe or when the cobalt-60 was formed by the decay of another nucleus. So very often what happens is you have alpha or beta decay producing something like this, and then it emits gamma ray photons to become more stable. Generally speaking, you're not going to see nuclei in nature that are in this excited state. Because if they were, they would have already settled down to a lower state by emitting those photons. So what are we going to get? Well, we're going to get the gamma ray photon. That's just how I write the gamma ray photon. Plus, it looks like we're going to have 60 on the top and 27 on the bottom. Wonder what that is? Well, it's cobalt. So how does the nucleus change? I'm not going to write all of this down. There will be some numbers here that you can write down if you like. How the nucleus changes is those 60 nucleons become more efficiently organized. It's a reorganization of everybody in the nucleus. The cobalt-60 nucleus loses mass. And I feel as though I shouldn't have to teach this to you. You should already know how to find the mass lost by the nucleus. The mass lost times the speed of light squared is equal to the energy released. We know the energy released because you're given the energy of the photon. Your only task, if you were to find the mass lost, would be to take that energy, which is in millions of electron volts, convert it to joules, then run it through E equals mc squared, and what comes out is your answer. And that's what I'm going to do on the calculator, but I'm not going to write these numbers down. So 1.1732 multiplied by 10 to the 6 mega is 6 or million. And I need to multiply that by the number of joules per electron volt, which is that number. This is the energy loss, and it's a big amount of energy. It's millions of electron volts. Well, a little over 1. I don't know why today I've gotten in the habit of writing mc squared equals E instead of E equals mc squared, but I hope that doesn't bother anybody. Delta M will be equal to that energy change divided by the speed of light squared. Again, it's energy that wasn't there before. So it's a loss of energy. Here's that formality thing. Do I really need to enter negative 1.87712? No. It is a negative change, but I'm not going to. So divided by the speed of light squared gives me a mass loss of 2.09 times 10 to the negative 23 kilograms. Thank you, Sasha. Gives us, that won't work. If I take that energy, sorry about that flub there, gives me a mass change when I divide by the speed of light of 2.09 times 10 to the negative 30 kilograms. So each nucleus that does this has that much less mass. May not seem significant, but it's bigger than the mass of an electron. Any questions about gamma decay? Okay, so on to positron emission, or positron decay, or what we call beta positive decay. I don't know if you noticed, but in some of the assigned questions, and I want to go back and just show this to you, in some of the assigned questions, like number 2, it didn't say beta decay. It said beta negative decay. First of all, if you ever see the phrase beta decay, it means beta decay. But there's another type of beta decay, which is called positron decay. And positron decay is beta positive decay. So if you see the phrase beta decay, it means beta decay, beta negative. Otherwise, you have to have the positive there. A positron is the antiparticle of an electron. A positron is a positive electron. It's identical to an electron in every way. If you could, and you can't, but if you could hold an electron in one hand and a positron in the other and feel the squishiness to each particle, you couldn't tell the difference. If you could see the color They don't have a color, but if they had a color, they would be the same. They have the same heft, they have the same shape. Everything about them is the same except one is positive, the positron, and one is negative, the electron. It turns out that for every type of particle in the universe, there is a type of particle called an antiparticle. That's not saying that for every particle there is a 1-to-1 ratio, that there's an antiparticle someplace. I'm not saying if we have this many electrons in the universe, you have this many positrons. I'm just saying positrons exist. There are antiprotons, negative protons. There are anti-neutrons. They're oppositely charged in some weird way that we will learn about later, even though the charge on a neutron is 0. Every single particle has an antiparticle. This was hypothesized close to 100 years ago. These things are incredibly rare in the universe. It just so happens, and you'll understand why, I hope, in a minute, that when our universe was formed, the matter won out over the antimatter. There is more matter in our universe than antimatter. And the reason for that is when matter, like electrons, comes into contact with antimatter, like positrons, they disappear. They annihilate each other. Literally, it means they cease to exist, and energy is produced in its place, photon energy. And for each particle that makes up the object, that touches an antiparticle of the other object, you get a photon. So if I have antimatter meeting matter, no more. That stuff doesn't exist anymore. So this is the type of energy generation that they use in engineering in Star Trek. A matter-antimatter reaction is going on. And it's, if we could do it, if we had a source of antimatter, it's a huge source of energy. Because let's just say for a second that we have a 50 kilogram Mr. Way meeting a 50 kilogram anti-Mr. Way. We would lose 100 kilograms of mass in a flash of photon energy. So how much energy would be created? Well, whatever 100 times the speed of light squared is, which is going to be 9 times 10 to the 18 joules. Kaboom. That's a lot of energy. Huge, huge amount of energy. That doesn't happen, though, because there's not much antimatter in the world. However, during positron decay, antimatter is created. So these particles are emitted during radioactive decay, and listen carefully, if when an electron is emitted, when a beta particle is emitted, you get an anti-neutrino, then you can remember now that when a positron is emitted, you get a neutrino. Right? So write the decay equation for the positron decay of nitrogen-13. You okay there, Erickson? Okay, just checking. So we have nitrogen-13. I can look up the atomic number of nitrogen. Why is that baffling me? Oh, there it is. Because it's not Ni, that's why it's baffling me. Nitrogen is number 7. That would be nickel Ni. And it's nitrogen-13. And it undergoes positron decay, which is this. It's a positive electron. I shouldn't write it that way. I should write it this way. Plus a neutrino, an anti-neutrino. When we start talking about antiparticles, and by the way, an anti-neutrino is the antiparticle of a neutrino. Anti is indicated by drawing a horizontal line over the top, so a neutrino is just that. Plus, well, we need 13 nucleons, and this bottom number is going to be 6. Because the bottom numbers have to add up. But listen carefully. The bottom number is not 6 because we started with 7 protons and we need 7 protons. How many protons are in this? None. There's no nucleons. That bottom number is not protons, it's charge. Sometimes it is protons, but not always. So then we look that up, and I think that's carbon. Okay. All right. I want to now talk about the net change. This has 7 protons and 6 neutrons. Just run that through your head. This has 6 protons and 7 neutrons. Yes? So the net change is that we lost a proton, and it was replaced with, I'm going to write it this way, a positive electron plus a neutrino plus a neutron. There's one final thing, I appreciate that, that we want to talk about here, which is sometimes called a decay and sometimes not. So I want to start off by telling you, forget about what's in the box. What's in the box, though, is sometimes given to you on exams and sometimes not. So if it's not, and it just says electron capture happens, and you don't know this, then you're in trouble. Electron capture is basically just what it sounds like. A nucleus captures an electron. And the difference here is that you're going to have a nucleus and you're going to add an electron to it. Whether you call it a beta particle or an electron, I don't care. So then it's going to produce some stuff. And I'm going to tell you right now, if you ask me what else is produced, I don't have it memorized, but I can tell you that it's going to be a neutrino. I worked it out. And I worked it out this way. I know that in a nuclear change, and I hope this kind of makes sense to you intuitively. In a nuclear change, when you have a nucleus and it emits an electron, then there's an anti-neutrino here, right? Well, to me, intuitively, it makes sense that if that electron were on the other side, the anti-neutrino would have to be the opposite of what it is. And I can't quite put my finger on why that makes sense to me. To me, it just does. That if you move the electron to the other side, then something's got to give. Something's got to be different. So anyway, what you are told here is that during electron capture, a stray electron is captured by the nucleus, and as a result, it's usually just an electron that's part of the atom. As a result, you get a neutrino and you get another nucleus. We'll talk about the last part here about the gamma ray photons in a second. So what's the electron capture equation for potassium 40? Well, we need to remember that it's capturing the electron. It's like adding a piece of copper to silver nitrate in chemistry. You would put silver nitrate plus copper on the left-hand side. We're adding an electron to things. What's produced? Well, let's deal with the nucleus. Nucleons have to be conserved. Charge has to be conserved. Boy, it's really easy to mess this up. It's really easy to want to put 20 somewhere instead of 18. Which is argon. And because this is the way it is, to conserve momentum, basically, you get a neutrino. The final thing I want to point out to you, and, well, I'll ask you this. I want you to look at the potassium 40 configuration, and I want you to look at the argon 40, and I want you to tell me whether we lost a proton and gained a neutron or we lost a neutron and gained a proton. Which one did we lose? Erickson, do you know? So how many protons are in potassium? 19. How many protons are in argon? We lost a proton then, because the number of protons went down. So what happened this time is that. And listen, you were able to do that for beta decay to find this net change, for positron decay, and now for electron capture. But again, I want to point out the mystery. We're done here with this lesson. This is electron capture. Beta decay, I'll write as beta negative. Beta positive, which is positron. Beta negative decay is this change. Beta positron decay is this change. Nope. Is this change. I just want to double check to make sure that's all right. Yeah. There is no way you can wrap your head around this and think of what's happening as pieces fitting together to produce other pieces. There's too many contradictions here. It's mysterious. Right now, you should be able to write decay equations for alpha decay, beta decay, gamma decay, positron decay, electron capture, loosely called electron capture decay, but that's wrong because it's not a decay. Not really. You should be able to predict how much energy is released given the right information, explain what's happening in all of them, including these three net changes. And each of these net changes involve another net change. It has to do with something called quarks that we will learn about on the very final day where we learn something new, the final lesson. What I would say to you is you should be able to do all of the questions attached to this now. Okay? Even going back to number 1. If you don't have the nuclear masses, you're going to use that data table that I gave you today. All right? So get to work. You still have about 15-ish minutes left. And Alex, when were anti-neutrinos or neutrinos discovered?
1956.
Okay, so I thought it was later than that, but 1956. Do you happen to know when they were hypothesized? And I'm willing to bet, I hope I'm right, that it wasn't that they discovered it and then tried to make it fit into their theories. They had a 1930. So the hypothesis was 1930. Way back in 1930, almost 100 years ago, they said, you know what? Our equations aren't matching reality here. Something's missing. Somebody puts up their hand. Hey, Chief, maybe there's another particle. Okay, let's call it an anti-neutrino. I'm exaggerating the chain of events, but that's what happened. Somebody hypothesized the existence of it, and then 20 years later it was detected. If nobody suggested it, it would never be detected. There'd be no reason to look for something unless you knew what to look for.